Thank you. Yeah, one slight precision before I start is that I'm here speaking because Jonathan Lebon, my colleague, wasn't able to make it to All Systems Go this year. But most, if not all of the work in this presentation is his, so you should have to him to all of this. I'm just presenting. Okay, so what are we going to talk about? The first underlying theme here, the first underlying technology, the main one is bootc. So bootc means bootable containers. It's both like a term for describing what the container images are, and at the same time the tools that is actually implementing all of this logic on the system. The main idea behind bootc, the main idea behind bootable containers is that you're putting everything that you need to create an operating system, to boot an operating system inside of an OCI container image. So it includes the general files of the system, and then it includes the kernel modules, the kernel itself, the initRD, the bootloader, shim, all of those bits. And you want to have everything inside of a single container image that you can consider as a unit, that you can ship, sign, etc., and use all of those tools. And that's like the main point of this, is that you can leverage all the OCI ecosystem that exists, and we use all of those tools to do things with the container image, with your system. So all the signing stuff, all the security scanners, all the registries, all of these interfaces, you can use that with bootable containers. All right, so bootc, if you were there last year at All Systems Go, we did kind of an introduction. Colin Walters, which is the primary author of the bootc project, did an introduction about what bootc was, how it worked, and all that, the concepts behind it. And it's been 1 year, so what happened? So the first thing is bootc got donated to the Cloud Native Computing Foundation. So it's like a big foundation of Cloud Native View. You might know a little small project called Kubernetes that's kind of related to that. And it's currently a sandbox project as part of the Cloud Native Foundation. The second item that got added to bootc is a new tool, which is called system reinstall bootc. And the point is that on some system, on some setups, on some context, you might have systems that are already installed using another operating system. And you don't necessarily want to go there and do a full reinstallation from scratch using an ISO or replacing a disk and all of those stuff. And so you want to replace systems on like literally live and reinstall them live to a bootable container system. And this is what this tool is helping you do that. So it's a collection of essentially, it's a tool that like does all of this for you, the repartitioning, moving files into the right place, etc., setting things up, so that you can convert a system that is using regular Fedora, CentOS, etc., package mode installation to a bootable container. The third point here is a feature that got added to systemd relatively recently, which is the soft reboot updates. And so support was added into bootc, or actually like OS3 underneath right now, but in the general bootc tool, so that you can update your system using bootc and ask the system to do a soft reboot update. It will only allow you to do that if you haven't changed your kernel and the kernel modules, of course, in the new version. So if your system has the same kernel in the current image and the next one, when you're doing the update, you can ask bootc to do a soft reboot update, and it will do that properly for you. And finally, the last point on here is that we're working on is adding a new backend to bootc to go away, to be able to sever ourselves from the OS3 path of managing the operating system. Right now, bootc relies on OS3, but we're adding a new ComposeFS native backend to bootc that will take advantage of all the ComposeFS features. So if you're interested in this one, like the next talk after that is going a little bit deeper into that. Yeah, it has plenty of integration for security that we'll talk about. Okay, so what we're here to talk here for this one is about the story for Fedora CoreOS. So Fedora CoreOS is an operating system that has been built initially from OS3, RPM OS3, from those technologies. It's been a while now. It's been about a little bit more than 5 years. We have been progressively, well, Jonathan has been doing the work progressively in the last few years to move Fedora CoreOS from this OS3 path into a full bootable container setup. So that's what we're going to talk about here. The first point is, so yeah, at the beginning, like 5 years ago, but like until 1 year approximately, we were everything OS3 because that's how the system was built. So when we were building the actual image for the system, we were using CoSA build, which is a wrapper then for the RPM OS3 compose tool, which takes a collection of RPM packages and build them into an image that we actually use to update the systems. So this image itself, it's an OS3 commit. It references everything that's going to be installed in your system. As we take security seriously, you signed this OS3 commit, and we signed it using the Fedora GPG keys, and we shipped that. So we were uploading that, all of the content, all the OS3 commit, and all the dependencies into the production OS3 repository in Fedora infrastructure. And then users would get that content via updates using RPM OS3, would download the updates. On Fedora CoreOS, the updates are coordinated by a tool that is called Zincati, and it will deliver the updates to systems in a controlled fashion. So the main idea is that you don't really want to update a fleet of hundreds or thousands of systems all in one go and all at the same time. That's generally not really a good idea. So what Zincati allows us to do is that even if we don't really have control of the systems that are running, of the stuff of the system from people that install Fedora CoreOS. We don't control what they are, where they are running, and what they are running. And so the idea is that we let them decide when they want to update things, when they actually want the system to be updated, and at the same time, we don't roll out the update to everybody at the same time. So progressively, we roll out the update, and the clients will fetch the update and actually reboot the nodes, etc., etc. That's what Zincati does. So all of this is very much OS3. There was no bootable container in this part. And so what has been happening in the past two major Fedora releases is that we started first moving things to bootable container, mostly as the transport mechanism. So we move the content from the OS3 commits inside of the bootable container images, the OCI images. And so you can see here the things in blue that the one that have changed. And so first we were still building OS3 commits, that part didn't change, and we were encapsulating them into container images. So we were taking the same results, putting them into container images. And then we would put that container images into a registry and ship that to users. So we taught Zincati how to switch from updating from OS3 commits into container images. And so that's how the first step that we did to move our fleet to bootable containers. The next phase that we did very recently for Fedora 43 release, which hasn't yet been released, so it's coming in a few weeks, is that we moved to actually building the system as a container. So instead of building OS3 commits, we're now directly building OCI, building the system as a bootable container inside of an OCI image. So we directly generate this OCI image. We don't take any intermediate step inside of it. And that's a really nice thing, and it makes builds of Fedora CoreOS actually be a container build. So it's a little bit special container build, but it's still a container build, and it's not a special tool that you have to learn and use around, etc. And finally, we move the signature from being inside of the container, being the signature on the OS3 commit, for now being outside. It's actually the container image itself that is signed. Right now, it's still using GPG, but we're trying to move away from that, but there's a few discussions around that. Okay, so what are the benefits of doing all of this work? The main one is that it significantly lowers the barrier to entry. So when you want to make a change, when you want to try out Fedora CoreOS, try and build an image of Fedora CoreOS, you can clone the Git repo and do a podman build, and you get a bootable container image of Fedora CoreOS. So the instructions are about just that. It's not more than that. The second thing is that it makes testing much, much, much easier. One of the problems that we had with OS3 is that it's relatively easy to produce one, but it's tricky to tweak, tricky to extend and do things with it. It's not impossible, it's just like you need to learn how to do it, and so everybody has very limited time, of course, and so there's only so many technologies that we can learn. So it was like yet another thing to learn, and so here the advantage is that when you want to extend a bootable container system, well, it's a container build, and a lot of people now know how to extend to run a Podman build or Docker build to extend a container image. So that's like a huge win here. The other thing is that when you have built this image, switching to it on a system is mostly one command away. You can switch to any other bootable container image that you have extended and push to any registry. And finally, yeah, so that's the building part. When you want to extend your system, you want to add a tool to it. You can do a container build, it's a regular one, run a dnf install command inside of it, and you will get a new container image that you can switch to, and with the tools that you need, whether it's for debugging or production. All right, so yeah, that's like the whole story behind it. It's the kind of the whole goal of bootable containers. The bootc project is leverage the whole OCI ecosystem that exists and reusing all of the tools that have been improving much faster than the one behind the OS3 project, which is good, but hasn't caught up in the same fashion. All right, so for Fedora CoreOS, yeah, this means a little bit what I've said here. Users are familiar with those tools for using them for the application container images, and so they can reuse it. The main ones are like the registry. There's plenty of registry available where you can push things and do mirroring. That's like a huge thing that for if you have disconnected environments, you want to be able to say, I'm pulling from this image name, but it's actually fetching from this other registry where I have mirrored all of the container images. That was something that is quite easy to do now with the OS3 images. It wasn't as easy to do with OS3. The other thing is signing. There's plenty of options for you to sign container images, keyless, manage keys, etc., all of the stuff with cosign that we can reuse here. Then, yeah, another side benefit of this is that by having a common shared base, by having those bootable container images, we can create a shared base between all the bootable container systems in Fedora. So in Fedora, we have multiple variants that are image-based operating systems. So right now, we're mentioning Fedora CoreOS, but we also have Fedora IoT. We have the Fedora Atomic desktops. That's like the main three ones that existed before this project started. And now with bootc, we're creating another base bootc image, that bootable container image that has essentially all the core tools, but nothing of the rest. And it's kind of like the core thing where you have systemd, the kernel, the classic tools, inside of it, but none of your apps or none of your specific server setups or none of the specific configuration mechanism. There's like no cloud in it inside of it, for example. And you need to decide what you want to put in it. So you decide how you extend it, how much you put inside of it, etc. And having this like core-based system that we can have, it makes for a really interesting testing target because we can say, hey, this is where we're going to make sure that things work. And then other variants in Fedora will be able to derive from that and make their own version on top of it. So, for example, at one point, we're not there yet, but we'll have the Fedora Atomic desktop rebase on top of this image, and they will benefit from all the testing that happen in this base bootable container image. Yeah, so lower CI costs and testing is like the big plus here. Now, if we want to dive a little bit more into how we're actually building those, images for Fedora CoreOS. We're using a few tricks related to the container builds, and so this is what is kind of like shown here in this a little bit simplified, but not too much container file here that we're using. One of the most common criticism with container file is that they are not declarative. So when you're building a container application, you're not actually correctly declaring what your container is going to be looking like, and it's only going to depend. It's going to depend on like what state the repos were in when you did the build, whatever the result of the command is going to be, and things like that. And that's kind of like a problem. But the container file itself, like it certainly does not pushes you into like a more declarative fashion, but it's still possible to do it declaratively, and that's like what we're doing with Fedora CoreOS. We're building the container image still in a declarative fashion while still using a container file. And so the first part here is that we're starting from a bootc image. So we're using those base images as the base target for our system, as a base building environment. We're copying in the sources of Fedora CoreOS, like the small configuration files that we have and a few other modules. And then we go and build the actual image. So we rebuild the entire container that we're going to be using as part of this container image. Then on the fourth line here, the second run, we rechunk the image. So that's like a special process that we have. Another common frequent criticism of container OCI images is that you have layers, but those are not well defined. Or usually when you build app containers, you may want to squash all the layers to make the image smaller or things like that. Well, with the bootable containers, like part of this flow is that we split the container images into intelligent layers. So we select which part we want to put in which layers, and we split the packages into those to get a result that is interesting. And this is what this phase does here. And finally, once you have actually built all those layers, well, we re-import them inside of our build process here with the from line. And then you had whatever labels you want, the version, you set the default command line, etc. And then you get your final container image. So yeah, so the build step, the step that builds the actual rootfs, it looks at declarative files. It looks at RPM history YAML files. What we used before we were doing that is what we used to declare what packages we're adding into our images. And we're still using that, but it's behind. It's a little bit hidden here, and eventually we might move away from that. But we're still using that because we progressively moving from the older version to the new one, so we can have a transition phase here. But the main advantage of those YAML configuration files is that they are definitely declarative. You're not like typing a DNF install command. You're telling the system that, hey, this is the list of packages that we're going to include. You can do version locking and things like that. So yeah, this is like the first part, and then it goes to the bootc based image tool, which actually rebuilds the rootfs with all the packages that you want inside of your image. And then finally, we run a few post-process scripts to tweak a few things, change a few certain exposure modules, and things like that, disable some units, etc. It's like maybe like the least declarative part of the image build process here. The build OCI, the build chunk OCI part, I've already talked a little bit about that. It's how we make the container image actually split into meaningful layers. So we don't just have one big layer that you would have to redundant every time you make an update. But the idea is that we create the OCI image from a given rootfs, and we split that intelligently. So we look at all the RPMs that are installed in this image, and we try and split them by version, if they have the same version, things like that. And there's a few heuristics that will generate essentially a layered image, which has, depending on your configuration, you can go to 50, 100 layers, that is intelligently splitting the content in your image. And that makes for much faster updates, because now you're just downloading the parts that have changed, and you're not redundant everything at the same time, all the time every time you do an update. And so yeah, this is where the Podman trick here is where we re-import this image into the build to get it to work. That's currently a Podman specific feature. And finally, a few caveats with all of that. We haven't really completed the transition yet, but we're very much quite far along in the process. We're still using RPM history right now on the nodes. We're planning to move to bootc to do the actual updates on the node, but there's still a few missing features in bootc, so we cannot do it yet. We have a few issues with UID, GID drift. It's kind of specific how we do some things, how we use NSS add files for the etc password group files. It's not due to bootc, but that's something we had before. We want to move away from signing using GPG, so moving to cosign. This is still in progress. As I said, we have a few bits of reproducibility, gotchas on the Linux processing, etc. But that can be progressively addressed. And finally, the updates are still slightly less efficient than they were with OS3, but hopefully improvements on this front are coming, thanks to some improvements into the OCI format itself. And that's it for me. Thank you very much.
We have time for questions. Any question? Yes, one question.
So I understand this is more or less still just a rootfs. Yeah. So an image usually has like more maybe UEFI partition, DM Verity, etc. So will this impose any restrictions on how we build final bootable images?
So the goal of bootable containers is that it does not define the layout on your disk. It defines the content of your operating system. Then how you actually install it on your disk is up to you. So we have tools that do it, like bootc image builders and things like that. Bootc itself can also do the installation. But the actual layout on the disk you control. So if you want to have this size partition, LVM, whatever, red, Lux, etc., you decide how you want things to be. And then bootc will install the files.
So the scope of the tool is basically to package a rootfs and not more.
And do the updates, etc., etc. Yes.
Mm-hmm. Okay, understood.
Like maybe something that just want to repeat, like we're not running the container. The container, the content of the container is installed on the system. It looks like a normal system, and then you boot into it.
Any other questions, comments? Yes.
How many layers are you looking at when on a chunked image and order of magnitude? And have you run into any performance problems, say big in an image with many layers?
So by default right now, I think it's about 50, 56 layers when you build an image. And it was because there was a bug somewhere that you couldn't go higher than a specific number. But you can go higher. I'm building images with about 100 layers right now. And it really helps with delta updates. Like you only update the part that matters. The main performance problem here is that the more layers you have, the more you have to pull in parallel as well. So it's kind of like a trade-off between networking, processing time, etc., and all those bits. I haven't seen other performance issues besides that.
Other questions, comments? Yes.
That's a follow-up question. Why is pulling in parallel a performance problem?
So it's not a performance problem. Like the more layers you have, the smaller they get. So if you want to get all of them faster, you need to pull them in parallel.
Yeah. Okay.
Any other comment, questions? Still 2 minutes, yes.
So how do you build this in an isolated environment? I assume you do this in Koji, or where are you building this, since you don't want to run this on some random GitHub action that will inject the next NPM supply chain attack?
So right now we're building them in Conflux. So it's another building tool that is based on Tecton pipelines running in a Kubernetes cluster. But you can build that anywhere. You don't strictly need access to network or anything. As long as you provide it with the RPMs, like repo files that points to RPM somewhere, you can build that in a constrained environment that only has access to the tools that you want. The builds in Conflux, like the work is in progress, that is to actually build that in Conflux, in a mode in Conflux that is lost the name, but it's like an offline mode, like in where you define what the inputs are going to be, they are verified, and then you never ever get access to network until all the builds is done. So like in a fashion, like you know exactly what came in, and you cannot curl anything in the middle and change the artifacts until the build is done and signed by the pipeline.
Okay, and how reproducible is that?
So that's indeed been a question work in progress and discussed a few times. There are things in OS3 in OpenOS3 that makes the system very reproducible, but they are indeed bits and pieces that are not yet completely reproducible. So I guess the question is, well, we're not there yet, but it's close.
All the time we have, so thank you, Timothée. Thank you.